Okay, so this is a problem that I'm not totally sure how to do. Haven't looked at it yet. Just wrote it down, but this sounds interesting. So basically, they're giving us two curves, let r equals 3 and r equals 4 minus 2 sine theta. Find the area inside both curves. Okay, so we're going to need to find, draw a picture, maybe figure out where they intersect to make sure we're finding the area inside both. Particle moves along the second curve so that at t seconds theta equals t squared. Okay, find the time t when the x coordinate is -1 on this interval. Okay. And then for the particle described above, find its position vector and velocity vector. Okay, interesting. So we're going to need quite a few things here. So finding the area inside both curves, we're definitely going to need this 1/2 times the integral from alpha to beta of r squared d theta, because that's the area of a polar curve. And so we're going to need to find alpha and beta. We're going to need to consider which r we're using, or perhaps if we're subtracting the two. For this one, it looks like we can do a direct substitution and just plug in t squared for theta. But then x coordinate, we're going to need to remember that x is equal to r cosine theta. Okay, and r is that, so we're going to need to write x in terms of theta and then in terms of t, right? Because t squared is theta, and then maybe set it equal to -1. And here, for the position vector, we're going to need to also find y, and remember that it's r times sine theta, right? And then we'll need to plug in our r and maybe take a derivative. So I actually think b and c might be on the simpler side in some ways, at least conceptually, or not conceptually, but sort of mechanically, and that a might actually be the challenging one for us. We'll see. So let us start by graphing these functions to see what they look like. So r equals 3, that's super simple because that's just a circle with radius 3. So at every angle, your radius is 3, which means you just have to stay at 3 the whole time. So that's r equals 3. Now, 4 minus 2 sine theta, again, I like to look at y equals 4 minus 2 sine x and think about what that looks like. Well, it's got a center line of 1, 2, 3, 4, then it's going to go up 2 and down 2. Okay. And it's a negative sign, it's been reflected. So instead of starting at the center line and going up, it starts at the center line and comes down. So it should look like this, where this is 2 pi, and that's pi, and here is pi halves and 3 pi halves. So it starts at 1, 2, 3, 4. So it should start out here at 4. By the time we get to pi halves, we're down to 2. So that should be here. By the time we're at pi, we're back to 4. So that should be here. By the time we're at 3 pi halves, we're actually up to 4, 5, 6, which is here. And then we come back. So it seems like it's going to look something like this. Okay, so that is r equals 4 minus sine theta. Okay, so this makes sense because they're now asking us to find the area that's in between both. So that is going to be this area. It's going to be this area, right? And this area, right? And then this area, right? Because it has to be in between both of them. It's sort of like their intersection. So one thing I'm noticing right off the bat is that a big part of this is just a semicircle, right? All of that area right there, that's a semicircle. So probably the easiest thing to do for that is just to use geometry. I'm also noticing that I could maybe just break this up into that piece, right? And then this piece here. Okay, so this whole piece right here of area is actually just part of that circle of radius 3. So if I could find this angle and find that angle, I could figure out what proportion of that circle I wanted, and then I could use my formula for area to basically use the other curve and use 1/2 times the integral from alpha to beta of r squared, because that radius doesn't change. So what I really need is I need this angle, right? What is theta? And what is theta here? Maybe we call this beta, and we call this alpha. Okay? So how do I find that? Well, I set these two equal, right? Because that's where they intersect. So if I've got r equals 3 and r equals 4 minus 2 sine theta, I get 3 equals 4 minus 2 sine theta. So subtracting 4, I get -1 equals -2 sine theta. Dividing by -2, I have 1/2 equals sine theta. And where does sine equal 1/2? Well, my special triangle looks like this. This is 1/2 root 3 over 2, 1. Here is theta, right? Because I'm looking for sine. That's pi sixths. So I think this one is pi sixths. That looks like pi sixths. And 5 pi 6. Now in the actual problem they gave you those angles, but I wanted us to have to find them by thinking about setting these two curves equal. And so we can see that that's pi 6 and 5 pi 6. So with polar stuff, your trigonometry has to be super, super strong. You end up with pi sixths. So now I'm trying to think how much of the circle, of the red circle here that we're trying to find this area right here, how much of it we actually need, right, to find that area right there. And well, we need to figure out how much to get rid of, and that's from pi 6 to 5, or 5 pi 6 to pi 6. So if we did 5 pi 6 minus pi 6, that's 4 pi 6, which is 2 pi thirds. So we don't want 2 pi thirds of the circle. So how much of it do we want? Well, we want 2 pi minus 2 pi thirds, which is 4 pi thirds. Right? That's the proportion of the circle we want. That's 4 pi thirds of 2 pi. So basically, I know that I need to take 4 pi thirds and plug it into my area of a sector formula, which is just 1/2 r squared theta. So it should just be 1/2 times theta times r squared, which is just 9. And so that right there should be, let's see, if this is 3 times 4, should be 12 pi divided by 2, which is just 6 pi. So normally it would be 9 pi, so it makes sense that 2/3 of it, or 4/3 of it rather, not 4/3 of it, 2/3 of it would be 6 pi. So I think that that makes sense. So this red area right here is 6 pi. Now we need to add, let me just check and see if that's the answer I got before. 9 pi halves plus 9 pi 6, I don't know, maybe. That'd be 4.5 plus 1.5. Yeah, I think that's 6 pi, I think that's good. So now for the blue portion, we've got a different radius, which is this r, and we want to integrate it from pi 6 to 5 pi 6 using our formula right here. So that area should be the integral from alpha to beta, which is pi 6 to 5 pi 6 of 1/2 times radius squared d theta. But radius squared is 4 minus sine theta squared d theta. So I'm not going to find that. You would have to find that on a calculator by graphing this just in your regular Cartesian coordinates, and then integrating it from pi 6 to 5 pi 6 and multiplying by 1/2. So if I add that to 6 pi, I should get the answer to A, which is the area inside of both curves. So just to sort of recap, we're using this formula, we're using some knowledge of geometry to think about the circle, and ultimately we had to find those angles by setting the two curves equal. So that's a little bit of a tough problem, but hopefully it makes sense. Now moving on to part B, a particle moves along this curve so that at t seconds theta equals t squared. Find the time t when the x coordinate is -1. I'm going to go ahead and erase this here. wish I hadn't erased my graph, but I can't really rewind the video when it's in real life. But I know that r equals 4 minus 2 sine theta, so then r equals 4 minus 2 sine of t squared, because theta is t squared. And I know that x is always equal to r cosine theta, so then x must be 4 minus 2 sine t squared, right? That's r times cosine of theta, but theta is t squared. So that is my x-coordinate in terms of t. My x-coordinate in terms of r would just be 4 minus 2 sine theta times cosine theta, but I had to plug in t squared for theta because now I want it in terms of t. And they want to know when the x-coordinate is -1. Well, I would need to solve this on my calculator. -1 equals 4 minus 2 sine t squared times cosine of t squared. So at that point, it's pretty straightforward to do on your calculator. Remember, here's r. So this is r in terms of t, because theta was given as t squared. But x is r cosine theta always. So that would be r cosine theta, where r is 4 minus sine theta. Plugging in t squared, you get this. Your x-coordinate anytime t. Then set it equal to -1 and solve for t. Then for c, it says for the particle described above, find its position vector. So we already have the x value, but the y value would be the same thing, except multiplied by sine of t squared. So because y is r sine theta, here's r in terms of t, and here's sine theta in terms of t. So I would write that, comma that, and I'd have my position vector. Now, velocity vector, I would need to take the derivative of both of these, which is kind of messy, but it's definitely possible. So that would be dx dt, and dx dt would be using the product rule. This times the derivative of this plus this times the derivative of this. So that would be 4 minus 2 sine t squared times the derivative of cosine t squared, which is negative sine of t squared times 2t, using the chain rule. Then plus the second, which is cosine of t squared, times the derivative of the first, which would be -2 times cosine of t squared times 2t. So that is dx dt. And dy dt, very similarly, would be 4 minus 2 sine t squared times cosine of t squared times 2t, plus the second, which is sine of t squared, times the derivative of the first, which is -2 cosine t squared times 2t. So it's just a little bit of calculus. And I think they asked you to find it at t equals 1.5, so then you could just plug 1.5 in. So that's one example of a polar question that involves calculus.